All right, so what I'd recommend for people in the back is to just move a little bit ahead so that you can hear the whole thing properly. Apologies for the hold up. We'll move on with the next session. Up next, we have Vladimir, who is a senior security researcher at Microsoft. He's done some amazing research with the CodeSys framework. He's also identified some bugs in the Windows driver of the SonicWall tool. His topic for today is From Dare to Discovery, how OSINT and modern recon techniques uncovered a global VPN infrastructure. This presentation has a complete attack chain that showcases some advanced reconnaissance techniques and some live demos. Here we'll run some practical methodologies that can help us do our OSINT skin, help us improve our OSINT skills, and put emphasis on the intelligence gathering process that can help you even proceed with other attacks. So please bring it up for Vladimir.
Thank you. Hello. Hope you can hear me. Yeah, okay. Thank you for joining me today. Today I'm going to talk about research I did last year. From Dare to Discovery, how OSINT and modern recon techniques uncover a global VPN infrastructure. Critical. A bit louder. Okay, yeah, I'll try that. So let's dig in. It all began one night while I played Deep Rock Galactic with my friends, and basically it's a game where dwarves roaming the cosmos, mining for minerals and killing bugs. And I played with two friends, Nikki and Philip. This is Philip. And basically Philip had some issues, some connectivity issues, some lags. And I asked him what's going on, and basically he said he installed new VPN, that one, and ExpressVPN, maybe you heard about it. And then we entered this chat about why should one use like VPNs, right? Security, privacy, stuff like that. And so I didn't believe him much about that. I said, not sure this is worth your while. And basically he dared me to prove him wrong, right? To prove that something is not good there. And so basically there I started looking at ExpressVPN drivers and different files. And one of the first things I found was the TAP driver, which is TAP adapter, which implements for Windows basically virtual network card, which will basically get information, wrap it, and set it to retunnel to other endpoint of the VPN, for instance, for the server. And basically I started reverse engineering it and opened the driver and found this nice piece of code, which initialized the miniport driver characteristics object, which has a lot of callbacks. And then the initialization happens with the Attendees register miniport driver. And so this object has a lot of callbacks that are usually used for different actions in the driver, sending messages, receiving messages, and stuff like that. One of them, one was that I actually look at was very interesting for me, was the miniport send net buffer list, which is the method that sends information, right? And so I dig into it, and basically the flow is pretty trivial. First, we have the validation for the adapter that is ready to communicate. Then we have retrieval of the first driver, of the first buffer, and then basically we will transmit this buffer in a loop for all the linked list of the buffers. And this is the TAP adapter transmit function. Basically what it does is getting a net buffer structure and allocates its data length plus 24 additional bytes. Then it gets the actual pointer from this net buff structure and copy the memory from this net buff object into the newly allocated data. I'll try another mic. Okay, is it better, folks? Yeah, cool. Yeah, let's do it. And so this is the prefix of the function, and before the end is allocate memory, right? Before this one. And this is how it looks. We can see the RS6 plus 18 exa, and then another. It's worse. It's worse. Yeah. I'll go with both. Yeah, cool. Let's do it. DEFCON style, right? Okay, so I hope they don't cancel each other. Yeah. waves stuff. Okay, so let me hold like that. And so this is the prefix. The idea is that we allocate a buffer and then we add 18 bytes for offset and then we add 18 bytes for size. And so obviously if we will give a big enough value, we'll have integer overflow. And so this is bad, but it's not really bad. Let's talk about what we can do with that. And so here we allocated the memory. Then we have the Attendees get data buffer, which is the pointer for the buffer that's been copied. And then we actually do the memory move, which is the copy of the data on the newly allocated memory, right? And so the idea is that we will allocate 17 bytes and then write it with a lot of data. And this is while kernel overflow. Now, generally speaking, there are some exploitation while kernel copy overflows, but they are hard. Why they are hard? Because there are tons of mitigations in the kernel to prevent this, and like modern HVCI, SMAP, stuff like that, even pagefall handler, device guard, stuff like that will make it very hard. Now, the issue is that this will be hard even for simple overwrite. For while kernel overflow, which is basically will overwrite a lot of memory, it's even harder. And so in this case, I just left it on the side and went a few days without thinking about it. And then I started looking at ProtonVPN source code, not source code, but on the driver again, and find the same bug, right? And so like I've already seen that. And at this point, I asked myself, do we have like a one-off issue, or is it like a systematic issue, something that is more bigger than two drivers? And obviously, OSINT is the answer, right? Because if we can search for it, we can find a lot of leads. And so, in this case, I just decided to create YARA rules to search for the problematic allocation of memory. And this is the part we want to search for. This is the assembly of it, and we can see that it's using the tag, the pull tag here, noted in yellow. And I just created a YARA rule to search for that for 64 bits and 32. And then I searched for it in YARA in VirusTotal and found 50 matches. Now. The cool stuff is that there are a lot of drivers with the same issue. And so at this stage, at this point, I just asked myself, or told myself that it's probably something that is widely used by a lot of drivers, something to do with VPNs. And and so like next question was ChatGPT, like what is the most popular VPN? And obviously OpenVPN is the answer. And so OpenVPN is really huge, right? It's used by tons of different VPNs, by ExpressVPN, NordVPN, CyberGhost, ProtonVPN, whatnot. And beside all that, it's a big repo in GitHub with a lot of sub-repos inside of it. We have the OpenVPN daemon, we have the EasyRSA, which is the implementation for RSA, also the GUI, top Windows 6, OpenVPN 3 Linux, which is the OpenVPN implementation for Linux. And basically at this stage I asked myself, okay, so we found this bug in a number of drivers, Windows drivers. Let's find some repo that relevant to that. And obviously I started looking at top Windows 6. And basically after some search, found this nice method, which does exactly that. And this is the issue we've seen in the assembly part, because it allocates the packet length from the buffer and then adds to it the additional header size with this macro. And so this is the bug, right? This is the source of the evil that we found in OpenVPN. And now, after we found the reason to look at OpenVPN, let's take a deep dive inside of VPN. We'll find some cool stuff there, I promise. And okay, first, one of the most interesting repos of OpenVPN, obviously, is the OpenVPN daemon, which is the process that will execute all the VPNing. Then we have the OpenVPN GUI, which is basically the GUI part that allows us to use OpenVPN on Windows. And we have the top Windows 6 that we've already seen. And for current session, this is the repos that are relevant and interesting for us. They have a lot more solutions and a lot more stuff to provide. So if you like to check them out, look at their GitHub page. Now, the client server architecture are pretty straightforward. We have the client that will be connected to the server, obviously SSL, MTLS even if needed, and the classical handshake, and stuff will flow on both ways. Now, on the single machine level, on the client level, we'll have the kernel space logic that will create a virtual NIC through which we will send data that will be wrapped and sent through actual physical NICs. And then in the user mode, we have the daemon that runs OpenVPN and actually decrypts messages and does all the VPNing. And so OpenVPN, in addition to being big open source, it's actually a standard for protocol of communication between server and client. And the structure of it, it's pretty straightforward. It can be over TCP or UDP. And first we'll have the packet length, 16 bits. Then we have the key ID, the opcode, which is the thing we want to do. And then we have the payload, which is pretty straightforward. This is an image of a handshake for OpenVPN protocol. Now, another very interesting part about OpenVPN is that it's supported on almost every big or small operating system and different architectures. You basically can open random router and find an OpenVPN binary there, right? And so it works on Windows, Linux, Mac OS, iOS, Android, and whatnot. And so the question is how they achieve that. It's pretty standard. They have a lot of includes with different macros and a lot of implementations for specific system, which allows them to be like dynamical and very fast and very efficient on the specific operating system. They be using a lot of macros, and then with different flows or different even functions and even different includes to do that. And so this is like the macro logic of OpenVPN. Now let's take a look inside other cool, interesting stuff of OpenVPN. One of which is the OpenVPN plugins. Now, OpenVPN have plugins to allow specific or additional credential validation or audition of the information, or even creating ETW events on specific logic that we want to do. All that can be implemented with plugins, right? And so the idea is that we have this DLL that exports some functions and can be called with. For instance, OpenVPN plugin OpenV1, which is the initialization function. In this example, they are setting credentials, and then we have the funcv1, which will basically do the logic that it needs to be done, and here we will validate for credentials. So down the line of plugins in OpenVPN, they are cool. They allow a lot of stuff, a lot of validation, auditioning, stuff like that. Now let's talk about the actual architecture of the OpenVPN service on Windows system. And so we have the OpenVPN server, which is the system level running service that has an open name pipe called OpenVPN/service. And process will connect to it and send information to this name pipe. How this will look on the OpenVPN server side, creating name pipe instance and then creating time to handle it. And we will validate stuff and basically create the relevant security descriptor for it. Then we will wait for connection. After connection achieved, the OpenVPN server will wait for get startup data, which is basically the way that other processes communicate with OpenVPN server. They will send a string that explains where they want to run the new OpenVPN process, the actual daemon that will do the VPNing. OpenVPN server will just managing those, and a lot of other instances of OpenVPN can be created. And so the startup data is the directory, the configuration, and the log file that should be executed, right? And so this is an example for initializing execution of OpenVPN programmatically. And after this startup data will be passed and validated and check that it's okay, the OpenVPN server will impersonate the connected client, and then it will validate that this client is the OpenVPN group of users, and then we'll proceed to basically create another name pipe, which it will pass to the execution of the OpenVPN process, right? And so then it will run this OpenVPN as the user that he has impersonated. And so this is how it looks on Windows. We have the OpenVPN server that through OpenVPN service got startup data and initialized and executed OpenVPN process. And then we have another name pipe, for instance here it's service 1234, through which OpenVPN will communicate with OpenVPN serve. And so the trivial question is, why do we need this another name pipe, or why so many name pipes? And the answer is that, for instance, if we have a weak client that connects to OpenVPN service and it wants to change some DNS configuration, maybe add some routes, you need to be able to do that. For that, and this is a weak user, for that it will send specific messages to the OpenVPN service, and the service will do it on its behalf, right? And so this is how it actually looks like. Through the same pipe to the inner pipe, we will get some data, and then we'll convert it to messages based on the type they have passed. Now, there are some logic that can be achieved with that. The client can send address message, or route message, or DNS configuration message, and then the server will send back acknowledge the message for that. So how it will look like? The OpenVPN will send a route message, for instance, for open service. The service will actually execute the logic for that, add another route, and then send an ACK message back to OpenVPN to signal that it has finished the logic. Now, if we want to take a look on the broader side of Windows, we also have the OpenVPN GUI, which will basically send the relevant data through the OpenVPN service to OpenVPN service that will initialize the daemon for the user. And now in the, let's call it like in the network level, this is the full architecture of the communication. We have the server with the plugin inside the OpenVPN daemon, and then information will pass through the plugin. The plugin can audit it, can log at it, and stuff like that. And now we can talk about first cool discovery that we found here. It's relevant to the potatoes class of vulnerabilities in Windows, and basically, potatoes vulnerabilities are vulnerabilities that allow, by exploiting some misconfigurations, some issues in Windows, achieve privilege escalation. And for instance, we have the sweet potato, which waits for WAPD queries on the network. It will answer the address for WAPD server, which will point to the attacker. Then the legitimate client will actually ask for WAPD, that file, which is the file that defines proxy on Windows. And then the malicious attacker will answer a bad WAPD file that points again to its controlled proxy. And in this case, the Windows client will start sending through that proxy different queries, and then the malicious proxy can require NTLM authentication, execute NTLM authentication, and do relay or track or whatever they like to, right? And so this is pretty much what will happen here. I'll show you a vulnerability and then how we can exploit to get local privilege escalation. So this is the logic in the service of OpenVPN that handles messages that received from the OpenVPN daemon. The logic is pretty simple. First, we'll have the amount of bytes we want to read, the peak name bypassing. Then we'll handle the message. In the handle message, we will allocate struct on the stack, and then basically we'll write onto this this allocated struct the amount of data that we read from the pipe, right? And so here we can see on the left upper part the amount of bytes we want to read. Then we can see that message is a union of structs, but basically it will be just the longest of them on the stack. And then we have the read pipe passing that will read the same amount of bytes onto the message struct. And so this is Stack Overflow, because if we can write more data than this message, we will overflow it. For instance, if you have the message header here with type and message ID, and then we have the address message or even the DNS config message, which is bigger, if we send more data than it contains, it will overflow it. And if we'll do it, we'll get fast fail stack cookies check failure, which indicates that we have Stack Overflow, but we had a cookie issue, right? Which is good and hard. So let's think about what we can do with the canary. This is the message, this is the function that handles the messages. And this is its prefix, and here we can see the security cookie usage. Now, basically, a security cookie defined here to be a value, and then what will happen is that we'll store it on the stack again, and in the end of the function, we'll validate its value and see that it hasn't been changed. Now, the actual interesting question is where it's being set, and so we have this security init cookie function, and this is the logic that happens there. And basically, first run will check if the security cookie value is constant and defined for first run, and then we do a lot of XORs with different information from the operating system, such as time as a file, performance count, and stuff like that. And the underline here is that it will be very, very hard to guess this value, and the only possible way to bypass that would be if we had read primitive on the memory of this process, but we don't have it, and so the underline here is that it will crash. If we'll overflow, we'll basically crash the process. Now, let's talk a little bit about some issues that are associated with name pipes. First, we have the classical name pipe instance race condition, which means that if a client connects to a server through a name pipe, if somebody creates the same name pipe with the same name before the server, the client will connect to it. Now, another issue is the superfluous pipe connectivity issue, which basically says that the client don't really know who is connecting to, and so the attacker that created the name pipe can do, for instance, malicious impersonation of the client. Now, let's sum it up in all of this together into a vulnerability, in a local privilege escalation vulnerability. And basically what we'll do, we create a malicious DLL, and then we will load this malicious DLL in OpenVPN daemon, and through the inner name pipe we will crush the OpenVPN service, and then the OpenVPN daemon will create the malicious DLL in the OpenVPN will create same name pipe and export it to other users, and then next user that will connect, it will connect not to original OpenVPN service but to our malicious plugin, right? And so the DLL main basically will extract the command line argument and deduplicate the handle that was passed there, and through that handle will send a malicious packet that will basically kill the OpenVPN service, which is just long enough data that will overflow the stack canary that we see. And after that, it will create the OpenVPN service name pipe and wait for connection. If a connection occurred, it will basically impersonate. First, it will get the startup data because this is the protocol. Then it will impersonate the connected client. If the connected client is strong enough, it will execute on its behalf, for instance, malicious application called driver communicator. And so this is the demo. On the right, we have weak user that executes the logic, and on the right we'll have the client that connects. Now on the right side here we had an exploit that actually sends malicious, that loads a malicious plugin and kills the OpenVPN service, and then runs with the name pipe and waits for connection. Then on the left side here, client connected to this unknownly because, well, it's the same name of the OpenVPN service name pipe. Then here we can see that we have very strong level process, for instance system level in this case, and yeah, take me a while to get there, but yeah, cool. Now this was cool because we got local privilege escalation, but the question is, can we do it remotely, right? And so the question is, how do we use name pipes remotely? And the answer is pretty simple. Windows have different mechanisms for sharing resources. In this case, name pipes are IPCs, resources. And basically, the idea is that there are some protocols for that, SMB and SMB2, and we will to use a specific resource for a specific endpoint, we will use an endpoint server and then the path to the share and the path to the resource. Now, we can do that, for instance, with net use, and we can actually then see the IPC's process, which is good, which means that we could potentially connect to remote endpoint and use its name pipe remotely. And so how would an attempt like that would look like? First, we'll see the tree connect request for the IPC on specific endpoint, and then we'll also can see this the request was declined because it's not that simple. And the thing is that there are some Windows definitions, some set of rules that allow and disallow connection to NAND pipes. For instance, we have the network access NAND pipes that can be accessed anonymously. By default, there are none such as that could be accessed anonymously. And another thing that we have is that we restrict anonymous access to NAND pipe, and this is enabled by default. And so the thing is that it means that it's very hard for us to do it without basically without credentials. But don't worry, we can get those. And basically, we should do that with reconnaissance. We can wait on the network and sniff for different hashes and then break them and get the credentials. And then this is not something new. Everybody uses, such as APT28, and then another processes exploitation by Mimikads, or even malicious plugins for different web browsers that doing exactly that. Basically, NTLM is NetLAN manager, a sort of protocols that allow us to connect securely, and this is how it will look like. First, we'll have the NTLM SSB negotiated request with the challenge. Then the server will send the challenge. Then the client will send back the NTLM proof STR, and in the end, we'll have the full hash in the packet. And we can capture that with tons of different tools. And I used here the responder in Kali. And basically, we can see that it captured the username, the domain, the server challenge, and the extra hash payload that actually hashes the password. And the other question would be, how can we crack that, right? And basically, there are tons of open sources there, and like the most two promise things that I found was Hashcat and John the Ripper, because they're widely used and very good. And I proceed with Hashcat because it's very good with GPUs. And first, I started with my own laptop, my gaming laptop that has ROGs that have RTX 3070 with almost 6,000 CUDA cores, and basically 6,000 CUDA cores for net NTLM v2 hashes will allow me to break something like almost 2,800 million hashes per second, which is pretty fast. And for starters, it's pretty good if you have very short password, right? If you have one char password, it will do it momentarily. But if we'll have a long password, it will take something like few years, and we don't really have time for that. Those are indeed rookie numbers. And so other thing I thought about was maybe we can build cool hardware to crack it. And we can do that, but it will take a lot more money and a lot more time, because to actually get a lot of GeForce, GTX, it takes a lot of time and a lot of patience. And so from here I decided to find another solution. Basically, I thought about how can I use cloud platforms for that. And basically there is this cool platform called Vast AI, which is basically allows you to rent machines with specific GPUs on time, for time. It's very, very easy to use. You got Docker images that can run on these machines, and it's pretty cheap, right? For instance, here we can rent a machine with 18 RTX 4090 for $8.50 an hour, which is pretty cheap. And now let's calculate quick math, as they say, the amount of CUDA cores and how much more such machine will give me in terms of cracking per hour, right? And so if my old laptop has almost 6,000 CUDA cores, the RTX 4090 have almost 2.5 times more, and the 18 times have almost 50 times more. And so the question is, like, will the improvement be 50 times more? And obviously not, because we have tons of different bottlenecks. But in the end, I proceeded with the big LUD, the machine with a lot of RTXs, and basically installed it and executed the cracking of a long password. And it took me less than 3 minutes to crack a 9-char password, which is pretty fast. And yeah, it's hell yeah for sure. And then now we have basically all the things that we need to create actual RC, right? Because we can firstly we used OSINT leads to find a basic issue, and then we keep digging into OpenVPN and found another issue, and then we understood that we need SMB enumeration and hash cracking to get credentials, and in the end we cracked those hashes with cloud cracking. All of this together allow us to actually get an RC vector, and the idea is that first we'll lurk on the network, wait for hashes, then recap them and crack them, and then we'll use them with NetUse to actually be able to access other PC IPCs. And then what we'll have in our exploit is actually connection to the remote endpoint namepipe of the OpenVPN service that we try to attack. After that, we will pass to it a malicious configuration and log on attacker-controlled share, as showed here. And so, in the configuration of OpenVPN, we'll have the directive to load a malicious plugin, which is again located on the malicious share, controlled by the attacker. And so, basically, first attempt, it didn't work because we need to allow anonymous access to the share and allow everyone to connect to it. And after these configurations on the attacker-controlled share, we got actually it working. First, we have the request for tree for share, then we have the request for the configuration, and in the end, we have the request for the malicious plugin that executes the logic. And this is the example of the demo that will first execute on the attacker-controlled share machine. Will execute the exploit, which will connect to the remote endpoint, and through the namepipe will load a malicious plugin from attacker-controlled share. And this is pretty cool because this allows me to actually remote code execute on the remote endpoint. In this specific example, it just dumped a lot of files on the desktop, which was pretty cool again. Now, the question is, can we like mount those two logics together? Can we execute the remote code execution and then the local privilege escalation? And the answer is yes. We just need to mount the LP logic onto the malicious plugin that we execute remotely. And in this case, after the malicious LP executed, we will execute the reclaim, the file that's called reclaim.warren kilos of error. And after executing this, we have an RCNLP vector. And the question is, what can we do from here? And some trivial attempts, some stuff that APTs love to do is bring your vulnerable driver. And then again, it will be pretty easy in this stage because we have already a PE. We can actually use the SC manager and create service with our malicious driver. For instance, we could use this one, which has read-write primitives into kernel memory, which make us very, very strong. And another technique we could use is living off the land, which is again used widely by APTs. Maybe find some installer MSI and mandel with it. And the classical approach could be even exploiting an 1 day or even new 0 day in Windows and Windows machines in a driver kernel. This is exactly what has been executed in this research, and I took it as well. Basically, the idea is to exploit an vulnerability in AppIDCs, which will change the previous mode and allow us to have arbitrary read-write into kernel memory. And other question will be, now what? Okay, so we have remote code execution, then we have LP, then we have even read-write kernel primitives. Now, APDs would love that because basically when you have executed some malicious logic on endpoint, you have a lot of anti-malware and antivirus application that will hunt for you. And what we would like to do, and general APD would like to kill those and bypass them. And so usually those come in the form of PPL, which is a protected process line, which was invented somewhere in Windows 8, if I'm not mistaken, which allows us to protect processes. The idea is that we will have a process that is digitally signed, and they have an hierarchy of different PPLs that are digitally signed. And the rule is that the higher the process, it can handle with lower processes, but lower processes can actually communicate with those processes. And usually, like the regular processes, even if the system can't actually affect the PPLs, right? And so what we'd like to do is abuse those read-write primitives to maybe un-PPL a process. How would we do that? Let's use WinDBG. Basically, there is this struct called PS protection, which indicates the PPL protection level of a system, of a process. And we can use, for instance, process directive to see the LSAS information, which is basically type protected, and it's a protected sign and win system, which is pretty high up the level, which means not much of different process can communicate with them and affect it. Now, if we'll try to kill a process, which is a PPL, we will fail, even if we are a system, because again, we are not a PPL. So if we have WinDBG, we could do it with actually overwriting the memory, right? We can find the memory, overwrite it, and then basically we'll crush the process in this case. Because if we'll overwrite the PPL field of winning, it's very high and important process, and it will basically crush the system. And now this will be our full chain. We'll use the RCE to gain code execution with a plugin. Then this same plugin we will execute the local provision escalation logic, the POC. And then with that it will wait and abuse the app ID sys flow to get arbitrary kernel read-write. And in the end it will, with those abilities, overwrite the PPL protection of a specifically WinInt for us to be able to crush it, right? And so this is the demo for that. Again, this is a remotely executed exploit that will connect to the remote endpoint on the IPC, on the OpenVPN namepipe service, execute a plugin. The plugin will wait for a connection. And here we can see the log that means the stage 1 and stage 2 loading of the plugin were successful. And then we'll have an user just executes the OpenVPN GUI, which runs on highly elevated privileges. And it will send the startup data to already our exploit. And then we'll have stage 3 and stage 4, which allows us to actually overwrite WinInt APS protection. And this gives us a full chain. And the question is, as I said, why an attacker would love to do this? Well, basically they have tons of stuff they would like to bypass. Security of OSs, antiviruses, stealth attacks, maybe they want to hide something, rootkits. And so this could be a pretty cool vector for attacker. And basically the Recon and the OSINT tool stack I used here was VirusTotal, Yara rules, Shodan and Zoom. I haven't talked about it in length, but basically those help me to find how much OpenVPN is used and popular, which is pretty much. And here we have the summary of the session. Basically the takeaways here is that first, one bug can be a pretty big deal. In this case, the plugin mechanism was implemented not on the best side, and allowed us to do a lot of damage. And another thing is that currently we don't really need to create heavy hardware system with a lot of GPUs locally. We can just rent some cloud from some cloud provider, and it's basically easier, probably more cheaper and available for everybody. And the third thing is that security researchers will probably use OSINT and Recon tools a lot because, well, we know that makes our life easier, and this is real romance between the two. And this is it. Thank you for joining me today, and I think we are finished. Any questions?